This video is going to recap the time lab that we did, as well as some little bit about the 2 of the 7 fundamental units we've encountered thus far. Our time lab was essentially an introduction to recording time measurements, and we used 2 different methods, the stopwatch and slow motion capture. And then we also had the calculated actual or true fall time that it should take something to fall a certain given height. And to practice these collecting of these types of measurements, we compared the fall time to the drop height. That was the objective. So comparing 2 measurement techniques and doing so by comparing fall time to drop height. That was our objective, so we did collect our data. Remember that we used a data table that you can organize however you want, but you should have units somewhere in that data table, preferably at the top of each column. And make sure your rows correspond to whatever the fall time is over there. So I'm calculating the actual fall time. I'm pretty sure I actually calculated that for this table. And the equation we use, which you don't need to memorize or know now, we just threw that in there because so that we had a standard to compare our measured times to. That equation is over there. T equals the square root of twice the height that something falls divided by g, which is just a constant value that describes how quickly something speeds up as it's falling. If we graph this, we get this kind of looking graph, and you can't really see my x-axis there, at least from my perspective right now, but that is the pattern of dots. It's 50 data points that are plotted, and you see that kind of curve. So notice that it's not a linear fit. Not everything we're going to do is going to line up straight in a diagonal nice line like some of our other labs have been. And so don't force that line of best fit to the data if you don't think you can justify it. Maybe you have some data points in the middle there that look like it's a straight line. Well, okay, you're working with the data that you have. But also realize that the more data we get, the better our trend will manifest and the better we'll be able to describe it. So more data is better. So I expect when I see some groups finishing a little early and they're convinced they have good data, well, let's collect some more. You might uncover something that other groups won't. And that's an important thing to share. One thing to know here is that the little alpha symbol down there that kind of looks like a fish without the rest of its tail, it's in quotes on the right side of my screen. That means varies. So when I say something like fall time there, I have the varies symbol that I've crossed out, and then height. The fall time, it does vary with height, but it doesn't vary directly like that. If it did vary directly, we would have that linear fit. Namely, like if I doubled t, then my height would double. Or if I doubled my height, my fall time would double. That would mean it varies directly, in a direct proportion. We in fact learned that it's not like that. It's actually the square of the time that varies directly with the height. And you can see that in my equation over there. That equation we use to get the actual or standard or should be fall time. If I square both sides of that equation, I get t squared equals 2h over g, and that means that t squared, the square of the time, varies directly with the height up there. And 2 divided by g, well, that's just a number because g is always some constant number. We're going to write out a little bit more of what that varies equation can look like. And so I have my original equation at the top left. I said, look, if we square it, that gives me it's the same equation, it's just squared on both sides, so it looks a little different. But it means the same thing, and that shows me that my square of the time varies directly as the height. So if I plot that on a graph now, that's when I get my linear or straight line equation. Because instead of having just time on the y-axis, I have time squared. And this is the process called linearization. You probably haven't done anything like this before, but in physics we do it a lot because it's really easy to look at linear graphs and it's really hard to deal with a lot of curved graphs. So when we do collect data and compare or find relationships between different quantities or things we can measure, which is what we said a lot of what we're doing is based on. Just comparing quantities, looking at relationships between things, and those things we put on the x and y axes. Well, it's nice to have a linear relationship. So sometimes we'll square both sides of the equation, and that'll give us a nice linearization or linear plot that we can then further analyze with like a slope or something. This is how a graph might have looked for my fall time versus drop height. Remember, what is on the first part of the something versus something graph title, that first part, that first something, is what belongs on the y-axis. And the second part is what belongs on the x-axis. So I had fall time on the y and drop height on the x, so my fall time versus drop height corresponds to that. So let's say I had some stopwatch time, so I'll made a little legend or key that indicates that. That's good to have on there. And then a lot of us, I said, take at least 3 measurements and find an average. So you could also plot each of those 3 stopwatch measurements per height, and you might get something like that. Notice maybe the higher we drop it, the more clustered our stopwatch times are. Usually that kind of thing happens. If you have more time, you tend to get better time measurements. Slow-mo times I put in blue. I'm just making up this data now. And then my green, I could have made a different color green for my true or actual or what my fall time should be based on my equation. Now, don't worry, we will derive this equation and use it in free fall, but here's just a great example of comparing those values. So we want to ask, this was in part a comparison of accuracy lab, what different methods or measurement techniques get us better results in terms of measuring time, because time's a hard thing to measure. We also want to be able to draw conclusions from our graphs, so like how does fall time vary with drop height? And we mentioned that in the previous slide. T squared varies directly with drop height, but if it's just T versus drop height, I get this little curve. And 3, we want to also be able to perform our conversions. We had started with some length conversions with our last conversion lab. We saw the slope was equal to the conversion factor. Now we're doing conversions in this lab that was actually converting number of frames to number of seconds, and the conversion factor in there was actually those frames per second of the camera that was recording the slow motion video. So as a reminder, there at the bottom, there's the number of frames divided by frames per second equals our number of seconds. And these are kind of the basic things I'm going to be looking for when, yes, we have a quiz, either tomorrow, Monday, Tuesday, whenever your next class is. So expect it just to be a rather short quiz, maybe not many questions, but we'll probably need to spend a little bit of time on it because I will be asking about graphing. Do we know how to label and draw our graphs, scale them appropriately if we're given some data, just like we had a warm-up question that was like, here's some data, make me a graph. Can we scale and label appropriately, plot the data accurately? Can we draw a line of best fit? Can we find the slope of that line of best fit? Can we find the y-intercept or estimate it based on one graph? And then finally with graphing, can we write that full linear equation, the y equals mx plus b format, where you substitute your slope you found in for m and your b, your y-intercept you found in for the b. After graphing, what else did we do? We looked at using that relationship on a graph to find a conversion factor. So I want to be able to convert units. After we do our graphing and find our linear equation, I want you to be able to convert units. So we looked at centimeters and inches, and we noticed there were 2 different valid conversion factors, 2.54 and 0.39. Those are 2 different valid conversion factors that you either divide or multiply by those depending on which unit you're going from and which unit you're converting into. Now, I'm not worried about you memorizing any of this stuff, but I do want you to be able to, if I give you a conversion factor, like there are 2.54 centimeters in 1 inch, and I say, how many centimeters are in 1,000 inches, I expect you to be able to tell me what that conversion is. Okay? Simple little multiplication or division operation, and then you show me your boxed answer of how many centimeters are in that amount. And we're careful that we're using a reasonable number of digits, not a decimal point with 7 digits after it, but a reasonable number of digits, and you're putting your units there, and you're boxing your final answer. We should also be able to do conversions for time, so like we did an example of how many seconds are in a year. We should be able to figure that out using our factor label method of conversion, or if you have another method you were taught for converting units, that's fine as long as it works. Convert it to the proper units, box it, reasonable number of digits, that's what I want to see. We should also be able to convert from number of frames to number of seconds, given the frames per second of a camera. Other than that, we're just going to ask maybe a couple questions about how we can interpret stuff from a graph, what kind of graph or line of best fit fits this data well. And from the pink data there in my stopwatch, it looks like it's probably more curved than it is linear, so we should be able to say a linear graph or a linear line of best fit is a straight line. Quadratic, well, that looks like a parabola. You know what that looks like. Exponential, that's going to be a different type of curve, but a curve nonetheless. So we should be able to name what those are. There's another one of our warm-up questions from a week or week and a half ago. Expect that kind of stuff on the quiz, graphing, conversions, drawing some conclusions from graphing and data analysis, and that'll be about it. Look back at the other videos. There were 2 others that can be helpful. Otherwise, we'll see you next time.